In this lesson, we are going to start discussing random variables. So first of all, a random variable is a numerical characteristic that's assigned to each outcome of a random circumstance. So for example, what a random variable could be the number of people in a sample of, say, 10 with type AB blood. But the kicker here is that it's a numerical characteristic. So in that case, if we have a sample of 10, the number of people who have AB blood could be anything from 0 up through 10. Another type of random variable could be how much weight you lose on a diet. The point is any kind of numerical characteristic. So it has to be numerical, as in not categorical in that case. Okay, and a family of random variables are all random variables for which the same formula is used to find probabilities. And once you know your random variable is in this family, you can then apply some general principles you know about that family. We don't have any examples of this yet, but we're going to learn one a little bit later in this lesson. An example of a family of random variables is the binomial random variable category. And once you know something is binomial, you can then apply this formula you know to find probabilities. Then there are two classes of random variables, and those last examples that we gave are kind of good examples of both classes. So the first one was the number of people in a sample of size 10 with type AB blood. That is called a discrete random variable, and this can take one of a countable list of distinct values. So discrete random variable. So the example above, the number of people with type O blood in the sample of 10, is an example of a discrete random variable. Another example could be the number of dogs owned by a random person. Even if your dog is missing a leg, it's still a whole dog. And on the other flip side, sort of a continuous random variable can take any value in an interval or collection of intervals. So continuous random variable. And some examples are height, weight, etc. So the first thing you should be able to do is list some examples of discrete and random variables, and then also, given some variables, tell me if they are discrete or if they're continuous. So for each characteristic, explain whether the random variable is continuous or discrete. So the number of left-handed individuals in a sample of 100 people, well, you only can have a whole number of left-handed individuals. It has to be either nobody or one person, 2, 3, all the way up to 100. So this is discrete. Time taken to complete an exam for students in a class. Well, you could take 55 minutes and 31 second, 31.7839246275 pi seconds. Anyhow, this is continuous. Vehicle speeds is at a highway location. Similarly to the exam time, you can kind of be driving at some random, really precise speed that contains a decimal and lots of numbers after it. So this is also continuous. And then the number of accidents reported last year at a highway location, that's an example of a discrete case. So for discrete random variables, we can find probabilities for exact outcomes, as in we are able to. So for example, we can find the probability that exactly 2 of the next 3 coin flips are heads. And for continuous random variables, you cannot actually find probabilities for exact outcomes. And we'll talk more about that in a later section. But the basic idea for these is you're limited to finding probabilities for intervals of values. So, for example, we cannot find the probability that a newborn's weight is exactly 7 pounds. It turns out that, theoretically speaking, it's technically impossible to be exactly 7 pounds. But we could find the probability that the newborn's weight was between 6.9 and 7.1, and which would give us a pretty good reason to believe 7 pounds was a reasonable guess. And if you wanted to get even closer, you could just make these numbers even closer together. Now, to work with discrete random variables, we'll start with those, and to do that, you're going to need to know some notation. So here is what we're going to use. X, this is the random variable itself. I.e., for example, number of dogs in a random house. We are assuming here that we're looking at discrete stuff. K, this is a specific number the random variable can take on. Specific number the random variable can take on. And the probability that x equals k, this is read P, probability x is equal to k. This is the probability that the random variable x equals k. So for example, if I was finding p of x equals 3, given that x was my dogs, this would be the probability a random house hold, we'll say, has 3 dogs, for example. And you should try to use this correct notation when writing your work so you can properly communicate what you're talking about. All right, suppose we find the probability that 2 out of 3 children born will be girls, and the next 3 births is 3/8. In this case, what is the random variable and what is the value of k? So 2 out of 3 children born will be girls, and the next 3 births is 3/8. So it seems like we're counting the number of girls in 3 births. So that's our random variable x. So x is equal to the number of girls in the next 3 births. Okay, and we're asked to find what is k. Well, we know that 2 out of 3 will be girls. The probability of that is 3/8, so we have specifically k is equal to 2, and thus that 3/8 is represented as the probability that x is equal to 2. That equals 3/8. So the probability distribution of a discrete random variable. So this is a function that, or like can be given as a table or just an equation or a function rule that assigns probabilities to the possible values of x. So for a discrete random variable, x, this is a table or a rule that assigns probabilities to all possible values of the random variable x. And when you have a finite number of, say, outcomes for x, then you can just list this as a table, but sometimes there's technically an infinite number of outcomes, or maybe there's n outcomes, and n is a variable that can get bigger, so in that case we're not going to list things as tables. So suppose that 35% of the students at a college are currently taking 4 courses, 45% are taking 5, and the remaining 20% are taking 6. Holy moly, these students are busy. Let x equal the number of courses that a randomly selected student is taking, and create a table that shows this probability distribution. So in the top of the table, we have our possible values of x, which are our k's. So k is equal to the number of courses that a random student is taking, and it looks like at this college, they're either all taking 4, 5, or 6. I don't know where they are, because when I was in school, I definitely didn't take more than 4, usually. And then in the next row, we're going to list the probability that x is equal to k. So in this first box, we're looking for the probability that x is equal to 4, or that the probability that somebody at this school is taking 4 courses. Well, that's 35%, which as a probability is 0.35. The probability that somebody's taking 5 courses, well, that's 0.45. And the probability that somebody is taking 6 courses is 0.2. Note that these numbers, these probabilities add up to 1. And that's because we have accounted for all of the different possible outcomes in the sample space. And because of all of these outcomes, all the probabilities of all the outcomes needing to add to 1 in the sample space, this will let you find some missing probabilities. So for example here, assuming that 1, 4, 5, and 7 are the only possible values for x, let's figure out what that question mark is. And just because I'm going to hate writing question mark, I'm going to write question mark equals x. So we know a 6th plus a 6th plus a 6th plus x needs to equal 1. Well, those 3/6 makes a half. So therefore x, or our missing value, has to be a half. Same idea, we're assuming here that our x can equal 1, 2, 3, 4, or 500. And once again, the missing probability must sum with all the others to 1. So we're going to let x equal question mark again. 0.1 plus 0.2 plus 0.3 plus 0.3 plus x needs to add up to 1. Well, all the numbers on the left add up to 0.9. And so therefore x has to be 0.1. So sometimes we care not only when a random variable is equal to a specific value, but when it is less than or equal to a specific value, or greater than or equal to a specific value. So, and the function that gives that is called a cumulative distribution function. So the cumulative distribution function for a random variable x is a table or a rule that provides the probability that x is less than or equal to some value k. And then to find the probability that x is bigger than k, you're going to actually use the complement, or something like that. So we'll talk about how to do that later in some later examples. But this thing is called the cumulative distribution function. And it's because you accumulate all the probabilities up to that k value. And the cumulative probability refers to the probability that x is less than or equal to some particular value. And an abbreviation for the cumulative distribution function often is CDF, just because writing those words, they're so long, it takes a long time. So for a large population, the probabilities for x, which is equal to the number of meals eaten yesterday, are given by this table. And we want to write a table that gives the cumulative probability distribution for x, or the CDF. So we're looking for a table that tells us the probability that x is less than or equal to 1, x is less than or equal to 2, etc. So here's how I'm going to do it. So on the bottom, just so it's completely clear what we're finding, I'm going to write probability that x is less than or equal to k. And up here are the x's or the k's that we're looking at. So first one, the probability that x is less than or equal to 1. So what's the chances somebody eats 1 or less meals per day? Well, that's if they eat 1 or less meals, at least according to this table, they just eat 1. So that happens at probability 0.1. For 2, we're finding the probability that x is less than or equal to 2. Well, if you eat 2 meals, less than or equal to 2 meals, you either eat 2 meals or you eat 1 meal. So this is 0.32 plus 0.10 or 0.42. And notice how this probability just accumulated the one before it. And then for 3, we're finding the probability that x is less than or equal to 3. Well, that's 0.1 plus 0.32 plus 0.56. It's the chances that somebody ate 3 or less meals. They ate either 1, 2, or 3. That adds up to 0.98. And for 4, px less than or equal to 4, you'd add up all the values in that table, and that's equal to 1. And I think it's pretty easy to convince yourself about what the pattern is here. So for example, this first value will always be the same as this first value. This last value, because it accounts for all possibilities of your random variable x, will always equal 1. And you see how this 2 is just the sum of these first 2 probabilities, whereas 3 is sum of the first 3 probabilities. So what is the value of the probability that x is less than or equal to the probability that a randomly selected person ate 2 or fewer meals yesterday? Well, you can either look at your table, or you could have just figured it out from first principles. If somebody ate less than 2 meals, they either ate 2 meals or they ate 1. And I should have said less than or equal to 2 meals. And that's 0.32 plus 0.10 or 0.42, which is also the second entry in our table that gave our CDF. You can figure this out either way. Just some random vocabulary before we move on, because it's good to be able to translate words into inequalities. If the question asked, what was the probability you ate at least 2 meals yesterday, what that means is that 2 meals is the smallest you ate. You ate 2 or more. So this means 2 or more. So that's the translation of at least. Or you can think at least means 2 is the least. In other words, it is probability that x is bigger than or equal to 2, which in this case would have been x equals 2, probability x equals 3 plus probability that x equals 4. You add all those up and you should get 0.9. Versus something like this. The probability that you ate at most 2 meals yesterday. Okay, so if you ate at most, that means 2 was the most. So this is 2 meals or less, i.e. that's the probability that x is less than or equal to 2, which we found above was 0.42. So it will happen in your homework that you have to translate this at least into an inequality and this at most into an inequality. So be familiar with that. A fair coin is tossed 3 times. List all possible outcomes and write a probability density function for the random variable x, which is equal to the number of heads in those 3 tosses. So listing the outcomes is like finding our sample space, so let's just call it S. So the outcomes could be all heads, 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 heads. You could have had heads, heads, tails, heads, tails, heads, and tails, heads, heads. It's nice to be systematic. So for example, I'm going to list all heads first, and then always to have 2 heads, and next I'll list always to have 1 head. So we could have had, we'll say, tails, tails, heads, which is kind of like the opposite of heads, heads, tails. We could have had tails, heads, tails, and we could have had heads, tails, tails. And finally, one more outcome is tails, tails, tails. And there are 8 things there. And we should just check and see, is 8 reasonable? Well, think about your counting principles. You're tossing 3 coins, 2 choices for the first coin, 2 for the second coin, and 2 for the third. Multiplying those together gives us a total of 8 possible events. So, looks like we got them all. Okay, now we're going to make a table that gives us the probability of having 0 heads, 1 head, 2 heads, or 3 heads, as those are the possibilities. So our k is equal to number of heads, probability that x equals that specific k. Okay, first of all, the probability that we have no heads, well, that's just this one outcome, tails, 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 out of 8 possibilities. So 1/8. 1 head, well, that's either tails, tails, heads, tails, heads, tails, or heads, tails, tails. That's 3/8. 2 heads is a similar story, also has probability 3/8. And 3 heads has probability 1/8. So there is your probability density function. A woman decides to have children until she has her first girl or until she has 4 children, whichever comes first. And we're going to let the random variable x equal the number of children she has. For simplicity, let's assume the probability of a girl is 0.5 for each birth. So write down the possible simple events in this sample space. So it's possible that she could have a girl on her first go and then have no more kids. If she has a boy on the first go and then a girl on time 2, or boy, boy, girl, and then has 3 kids, or boy, 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 and then gets lucky on birth number 4, or just has 4 boys and decides that 4 children is enough and she's going to stop, even though she didn't get a girl. So there are all of these simple events in the sample space. And the value for x will be the number of children she has. There's 1 outcome with 1 child, 1 outcome with 2, 1 outcome with 3, and 2 outcomes with 4. Next, we're going to find the probability for each of the simple events in this sample space. So I'll make a table that has my event and then computes the probability below. So if the event is that she has a girl, that has probability of happening 0.5. For the boy-girl birth, well, these births are independent, we're assuming, so we have 0.5 times 0.5, which is equal to 0.25. And then next there's the boy-girl birth. Well, that's 0.5 times 0.5 times 0.5 times 0.5, which is 0.5 cubed. And then keep all the digits here, don't round these. This is 0.125. And then two more outcomes, boy, 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 girl. Well, that's 0.5 to the fourth. Just happens with probability 0.0625. And then the final one is boy, 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 0.5 to the fourth, 0.0625. And if you just want to make sure that you're correct, you could add these probabilities up, and they're going to sum to 1. The final two sum to 0.125, and then 0.125 plus another 0.125 is 0.25, and then it's pretty obvious that you've got 1 here. Now, this is not our probability distribution function of a random variable yet, because our random variable x was the number of children she had, and these two outcomes, the boy, 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 girl, and boy, 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 are the same in terms of number of children. So find the probability distribution function for x. So k equals number of kids. Find the probability the random variable x is equal to that specific number. So she could have 1, 2, 3, or 4 children. So to have 1 child, that means she has to just have that girl in the first birth. That happens probability 0.5. 2 kids, that's the boy-girl birth. That happens probability 0.25. 3 kids, that's the boy-boy-girl. Happens probability 0.125. And with 4 kids, either she has boy, 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 girl, or boy, 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 boy. So this is 0.0625 plus 0.0625, which adds up to 0.125. And that's our probability distribution function. Okay, let's draw a picture of this probability distribution function. So we're going to draw a bar graph. Okay, so on the y-axis, we're going to put the probability that x is equal to some specific k value. So we'll have this be 1 child, this be 2, this be 3, and that be 4. Okay, and the highest probability is 0.5, so let's just call this 0.5. Half of that is 0.25, and then half of those halves is, well, the lower half is 0.125. So the chances of 1 girl were 0.5. Two children happen probability 0.25. 3 children happen probability 0.125. And 4 children had the same probability as 3. So there's our picture. And on this axis, capital X is equal to the number of children. So explain which would be of more interest in the following situation: the probability distribution function or the cumulative probability distribution function for x. If you think both would be of interest, explain why. So a politician wants to know how her constituents feel about a proposed new law, and she hires a survey firm to take a random sample of voters in her district, and x is the number of sample who oppose the new law. So this person might make their decision to oppose or support this law based on how they feel. So if she's going to support this law, less than a majority have to oppose it. So in this case, that's a cumulative. She will want to know when the percent who oppose the law is less than or equal to 50%. In other words, she might want to know probability that her x value is less than or equal to 50%, as opposed to what's the probability that this equals exactly 50%. She wants to know when is it going below this, and in that case, once fewer than 50% of people oppose the law, she'll probably decide to support it. Each time someone is exposed to a virus, he or she could become infected with it, and we're going to let x equal the number of exposures a person has prior to becoming infected. For instance, if x equals 0, the person became infected on the first exposure. If x is 1, the person became infected on the second exposure, etc. So in this case, what probably would be more interesting is the probability density function. Although you really could argue both in this case if you wanted to. But what this would tell you the proportion who get infected on exposure number x. So the proportion who get infected on exposure number x. So for example, suppose your x ranged up to 5 exposures, you could see what proportion get infected on the first exposure, second exposure, etc.